Hello everyone, today we are going to discuss 1D steady state heat conduction without heat generation through a plane wall. Now consider general heat conduction equation in Cartesian coordinate. A governing equation is applicable to a control volume in which temperature gradient exists in all three mutual perpendicular directions which are x, y and z. Hence, heat transfer rate or heat flux takes place in all three directions which are qx, qy and qz. Now for this control volume there is a heat generation within the control volume and there is a heat storage within the control volume. So temperature is a function of three space coordinates and time for this control volume for which this governing equation is applicable. Okay, now if the material of the control volume is homogeneous and isotropic and the thermal conductivity is not varying with temperature, then thermal conductivity is constant. If thermal conductivity is constant, then this governing equation is to this. Okay, but this governing equation is applicable, both these governing equations are applicable for the 3D flow. Now our problem is 1D problem. 1D means temperature gradient exists only in one direction and heat transfer takes place only in one direction. It means heat transfer in y direction and z direction is 0. Similarly, these two terms in the equation will be cancelled. Secondly, our case is steady state problem. Steady state problem means temperature do not vary with time. If temperature is not varying with time, then this term in this equation and this term in this equation will also be 0. Now third case is without any heat generation, considering that there is no any heat generation within the control volume. So this term will also be 0. Okay, now we are left with only this term, del square t upon del x square is equals to 0. Now for 1D flow our problem is converted from this to this. Now consider a slab in which temperature gradient exists only in one direction. It means the temperature at any point on this face is T1. Okay, and temperature at every point on this face is T2. There is no variation of temperature along this direction and there is no variation of temperature along this direction, which is height and width. And consider the thickness of this slab is very less as compared to the other two dimensions. It means L is very less than H and B and T1 is higher than T2. It means heat will flow from this phase to this phase. Now assume this condition like this. Now suppose this is the first phase and this is the second phase. It means the temperature of any point on this phase is T1. There is no variation of temperature on this phase, and similarly temperature at any point on this phase is T2. Now temperature may vary from one cross section to the another cross section in x direction only. It means if we put a third cross section between these two plates, the temperature of this phase, which is at a distance x from the left face, will be T, different from these two, but there will be no variation of temperature within this cross section. It means when we consider a cross section at a distance x from the left face, okay, so the temperature of this complete phase again will be T. Okay, so this is our 1D problem. As I discussed earlier, for the 1D problem the governing equation is reduced from this to this. Now we are left with d square t upon dx square is equal to 0, and I already told you that temperature is a function of x only. Temperature is varying in x direction, there is no variation of temperature in y and z direction, and also temperature is not varying with time. So temperature is not a function of time, and other two space coordinates temperature is only function of one space coordinate, which is x. After integrating this equation, we will get dt upon dx as C1, where C1 is the constant of integration. It means temperature gradient. dt upon dx is showing the temperature gradient. It means temperature gradient is constant, which means temperature gradient for this problem is linear in nature in x direction. Okay, now after further integration, we will get T is equals to C1x plus C2. Now, as I already told you in this syllabus, our complete motive in heat transfer problems are basically to determine the temperature distribution and the heat transfer rate. So from this equation, we can determine the temperature at any point within the our system. So to determine the value of constant of integration C1 and C2, we need to specify two boundary conditions, which are at x is equal to 0, t is equals to t1. It means we are taking origin from here, and this is the plane which is showing x is equal to 0, and this plane is showing x is equal to L. Okay, so according to the boundary condition, at x is equal to 0, T is equal to T1. The temperature of this phase is T1, and the second boundary condition is showing that at x is equal to L, T is equal to T2. The temperature of this phase is, this cross section is T2. Now substitute this value in the equation number 1. We will get the value of constant like this: C2 as T1 and C1 as T2 minus T1 upon N. After substituting the value of C1 and C2 in the equation number 1, we will get the temperature distribution like this: T2 minus T1 by L into x, this is the value of C1, plus T1, which is C2. Now after rearranging, now as we already know, heat flow always takes place from the higher temperature to the lower temperature. It means temperature at any other cross section when this thermal system will be lower than the temperature of T1. Hence we will rearrange this temperature distribution equation in order to show that the temperature is lower than T1. So after rearranging T1, and we have taken minus common from this term, so T1 minus T2 upon L. We have completed one part of our basic analysis of the 1D problem, in which we have determined the temperature distribution within the thermal system. We have to put only the value of x, distance of the cross section from the left face, and we can determine the temperature of every possible cross section in this system. Now this term is basically showing temperature gradient within the system. Okay, now we can see that temperature gradient is linear in nature. So I already told you in last lecture, for the temperature gradient within the system to be linear, 4 assumptions are applied. So we have applied all 4 assumptions. First one is problem is steady state. Okay, second, there is no heat generation. Third is that thermal conductivity is constant, and fourth one is that the area is constant, which means the problem is plane wall. So after these 4 assumptions, Ax is equals to constant, thermal conductivity is constant, okay, heat generation is 0, and problem is steady state, we will obtain the linear temperature gradient within the system. We have already discussed earlier, the basic objective of the analysis of the thermal system is to determine the temperature distribution and the heat transfer rate. Up to now we have determined the temperature distribution in our system. Now we are going to determine the heat transfer rate. As we already know from the Fourier's law of conduction, heat transfer rate is given as minus Ka dt upon dx. Temperature gradient dt upon dx is given as T2 minus T1 upon L. After taking minus common, we will get heat transfer rate as Ka T1 minus T2 upon L. Now, as I already told you, to simplify our analysis, we introduce the concept of the thermal resistance. As in electric circuit, current flow is given as the ratio of voltage difference to the electric resistance. Similarly, in our thermal circuit, which is analogous to electric circuit, heat transfer rate is basically given as the ratio of temperature difference divided by thermal resistance. If we compare our formula of heat transfer rate with this, we can see that this quantity L by Ka is basically equal to the thermal resistance RTH. Now if we draw the electric circuit, then temperature difference is the cause of heat flow. So heat flow takes place from higher temperature to the lower temperature, and the thermal resistance of the system is given as L by Ka. Now we are going to discuss a problem from GATE 2014 based on the 1D steady state heat conduction. According to the problem, a plane wall has thermal conductivity of 1.15 watts per meter Kelvin. It means the plane wall it is having thermal conductivity K as 1.15 watts per meter Kelvin. Now further, if the inner face is at 1100 degrees centigrade, it means the temperature of the inner face is 1100 degrees centigrade and outer face is at 350 degree centigrade, and the temperature T2 is 350 degree centigrade. Now further, design the thickness of wall to maintain a steady state heat flux of 2500 watts per meter square. Okay, now we have to determine the value of thickness of the wall, which is L. Okay, to maintain a heat flux Q as 2500 watts per meter square. Okay, so we need to determine the value of thickness of the wall. As we already know, heat transfer rate is given as T1 minus T2 divided by L by Ka. So heat flux, which is basically heat transfer rate per unit area, will be given as T1 minus T2 divided by L by K. So in this formula, we know everything. T1 is given as 1100, T2 is given as 350, thermal conductivity K is given as 1.15, and heat flux is given as 2500. Only unknown is L. After solving, we will get the value of the L as 0.345 meter. It means the wall thickness of the wall should be 0.345 meter. Okay, we will stop here. Thank you everyone.